Well, it's a pleasure to be here. We're in the middle, as you know, in a knot theory and teaching summer school conference on knot theory. And some of the things that I'm going to talk about here are actually reflections of things that are happening in the summer school. They're reflections of some of the more geometric things that knot theorists are thinking about. I don't intend this talk to be particularly technical, but it will show you some aspects of things that are real research problems. Let's just begin. I've called it physical knots because I'm going to be emphasizing how knots come from physical things and go back to them. After all, we're talking about knots, and knots are patterns that occur when you tie something on a rope. And for us, we look at them in a kind of a scientist's way, so we make the knot and then we try to understand how it's working, you know. And of course, you could, even if you're doing practical knot tying, think about how is the knot working. For example, if you splice two pieces of rope together, you may know more than I about different modes of splicing, but this is probably the simplest mode that everyone knows, the figure-8 knot mode, where you have two loops and each loop is grabbing the two base strands of the other loop, and so when you pull it, it tightens. And you can understand physically how that's working in terms of the friction and everything, that this works well, and if you put force on it, it won't slip away. And so there are many issues that are really quite physical about knots. But then there are topological issues, which is the first sort of thing that mathematicians began to think about. What I mean by topological issue is the following. Suppose that I were to tie a knot in this rope, in the sense of a knot in the middle of the rope, and then I splice the ends of the rope together. And in this case, I do it by the craft of knot tying, but we could have embossed it some other way. But now we have a closed loop of rope, and I'm not worrying about this knot. This knot I've just used as craft in order to tie the rope together into a circle. But now I have this circularly interconnected loop of rope in space, and the question is, and it's of course obvious to you, that it won't be undone. There's nothing you can do to get rid of it. But how do you make a mathematical model of such a thing and then prove that you can't get rid of it? And on the other hand, there are, and I will show you a little film, but I thought I would do it by hand. It's very easy to be deceived about this sort of thing, and we're curious about why that's the case. You see, I tie a knot in the rope, and then I tie another weaving in the rope above it. So in fact, what you see here is the figure-8 splice that I mean the one that I had before, and then I make it a little more complicated. Like that, I weave it a little more complicatedly. Now it's even more knotted than it was before. And then it seems as though, weaving it one more time, I've made it even more complicated than it was before, and I find that it isn't knotted at all, you see. And that wasn't a sleight of hand, that was just the way it is. The way it is that it's very difficult to tell when you have a knot in front of you whether or not it is indeed knotted or not. So there are many questions, mathematical questions of that kind, abstract mathematical questions about whether two knots are the same, or whether a knot is trivial in the sense of being untieable, and so on. And the thing about that is that we can make good models of this, which are genuinely faithful for what ropes do. And I just wanted to say a word about that because it's actually kind of remarkable. Elementary mathematics, you have the numbers, 1, 2, 3, 4, and the numbers are, in fact, an excellent model of multiplicities. So that if I look down on the desk and I ask, how many pieces of chalk are there on the desk, I can go ahead and count, and it will be reliable if I'm careful. There's a great reliability between our model of counting and the model of the way individuated entities occur in the world. But these are continuous entities, and they're rather crude. You could make ropes in lots of different ways. And we put a topological pattern into the rope by making a knot. And then it turns out that as far as the topological part is concerned, the part about just deforming it one way or another and maybe deforming it into the same pattern as another one, that we have an excellent model for. What we don't have great models for is exactly how they behave physically. That's much harder. So it turned out that the more abstract part had a good mathematical model, as good really as the model of numbers is for multiplicities in the world. So there's something to think about there, but I don't want to stay philosophical throughout the whole talk. So let's look at this slide, and then we'll go on to the next one. This is an Escher print, and you may be aware of it. What Escher has done is he's cut out some parts decoratively, and he's also cut out this middle line going around through this 3 half-twisted Mobius band. Half twist, half twist, half twist. You could make this yourself. The band, if you imagine putting all this back in, all this cutout, has one edge and one side. It's harder to point to the fact that it has one side. It's a Mobius band. And if you cut the Mobius, 3 half-twisted Mobius band down the middle and look at it, and that's what Escher has put in front of us, you see that you get a knot. There's the knot, right? So that's an amazing fact, and it's more surprising if you should do it yourself, so I recommend it. Take a piece of paper and twist it, 3 half twists, tape it back together. Now you have the 3 half-twisted Mobius band. Now take a scissors and cut it down the middle, and it falls apart and becomes a knotted band. And it always seems surprising every time to me when I see that happen. So I recommend it to you. Let's go on. Here's that other theme. I don't know how visible that is. From here it's a little pale, but I've drawn for you using a program called NotPlot. Due to Rob Shrine. I've drawn, which is available in case you're interested in making pictures and experimenting with knots. NotPlot, K-N-O-T-P-L-O-T. This particular one looks pretty knotted, and so I leave it to you as a kind of puzzle as to whether indeed this is knotted or does it come apart the way the demonstration I did a moment ago came apart. And if you're interested in that, and we have a little time after the talk, I will show you how NotPlot lets you find out about the knottedness of this particular configuration. Now, here's the one I did for you. I know it's too far away to show you that trick, so I'm showing it to you again. And this time, this is the question, the knot in question that I asked you whether it was knotted or not, the one I held up. And here is a little movie of the making of it. This is what I did just a moment ago, but maybe you can see it better this way. There's the square knot, and then I seem to make it more complicated by dropping it through the bottom part, and then I make it even more complicated by pushing it through the top loop. And now my hands are far apart from the knotting part, and I'm pulling on it, and it seems to be going away. So how do you predict things like that? It's very hard. We don't actually know. I mean, we don't. We don't know how to look at something and tell whether it's knotted or not. We have some ways to calculate things, and they're rather strange, and I'm not going to go into them, but I thought I'd tell you what it looks like. You take that thing and you write down some information about it, and then you do some mathematical operations on it, and you end up with maybe a polynomial or something like that, or a number. And if that number or polynomial is not trivial, then you know, in some sense of trivial, then you know that the thing was really knotted. But what happened in the in-between of translating it from the geometry to this other thing, number, polynomial, other mathematical object, you lose track of the intuition you had about it, and so you really don't often know what happened. And so it's a very mysterious subject. Now a couple of more things about tricks. Excuse me, I want to just get back a little bit here without knocking all the wires down. That's better, I think. This is a trick I devised, copying a certain kind of trick that was invented by Sam Lloyd, a puzzleist. I seem to be doing ordinary topological moves. I push this little loop here, and then I push it through, and then I push it back through, and then what happened? Well, I slid this one this way, and this one this way, and they formed a little loop all by themselves, and they came out, and then this reconnected over here, and it reproduced itself. This is just playing around, of course. But it might be a kind of biological playing around, right? In biology, things do get cut and recombined, and we'll come back to that in a moment. Here it's just a visual trick. Here's another bit of applied knot theory for you. Suppose you wanted to make a circuit, as there are circuits, which has a bunch of switches, maybe 3 or 4, one near the door and one inside the house and one upstairs and one somewhere else, and each one of those switches is supposed to turn the light at the porch on or off. Now you can use Boolean algebra, if you happen to know that, to design arbitrary logical conditions on switches. But I'm jumping across the Boolean algebra and making a topological kind of solution here, because what you see up here is a 3/2 twisted Mobius band, just like the Escher drawing, and you see that that forms a knot. It's not a band, I'm just drawing the boundary. So it's a 3/2 twist, though, and it's all connected. And so that means that in this condition, if I put a little circuit from here to here, battery, bulb, then then the electrons can flow around and come over here, and the bulb will be on, right? Now, if I take one of these and I switch it so that it goes from this condition to that condition, well, then there will be 2 of these, and these will not be connected to one another, and it doesn't matter which one I switch. And if there are an odd number of them that are crossovers, then the light will be on, and if there are an even number of them, then the light will be off, and you can have as many of those switches as you like. So you need double pole, double throw switches connected in that pattern, and you can put as many of them as you like and control that light. If you happen to know Boolean algebra and you know how to design these things, you'll find that you get an exponentiating expression in the logic that needs to be simplified, and you might not find this. You have to look very carefully in the Boolean algebra to discover that this is what the Boolean algebra might be telling you. So this is an example of applying knot theory by abduction, going up beyond some logical structure. All right. Now we're changing topics, and we will be changing topics every few minutes here because I'm giving you a survey of some ideas and how they relate to different things. This is a famous photograph, electron micrograph, due to Stasiak, Spengler, and Cazarelli. I hope I have the right number of collaborators there. Back in the 80s, one of the first photographs of knotting of DNA. And what was done was, there's a DNA molecule, a closed circular DNA molecule, and it's been coated with protein, so it's quite thick. And the electron micrograph can then show the geometry of it. And then you can look at it and you can see that apparently it goes over here and under here and over there and so on. And there might be some ambiguity on your part, but the people who looked at it carefully made some decisions that are close to what your eye is making and decided that it was in fact woven in a certain way. And in any case, I think in this case, if you thought that one is ambiguous and decided that maybe it's one way or maybe it's the other way and all the rest are non-ambiguous, you would find that it was knotted in either case. It's a proof that DNA can be knotted. And the beginning of a whole long train of research about topology of DNA as a result. So here is what looks like to a person who draws who draws figures on the plane, like the ones that I had a couple of slides ago with pencil and paper and little drawings like that. This looks like that, only it's been drawn by the electron micrograph, and it looks like a knot diagram, and we could sketch it if we wanted to and play with it, or we could make it out of rope. So we can bring something which is down in the micro world, structure down in the micro world, through this pattern up into an ordinary everyday space and examine it. So what I've done here, I see there's a little light going across, but it probably doesn't bother us too much. This is the original picture on the other slide, and this one is just a rotate of it. And over below here is a table, a relatively modern table, of all the knots up through some number of, it's not really all the knots up through 8 crossings, but the tables go like this. So it's certainly complete up to 7, and then there are more 8 crossing knots going on. So the first knot is the unknot, and the next one is this little trefoil, and the next one is this figure 8 knot, and so on. And you walk up the table, and I could ask you, where is that knot on the table? Maybe I should give you a moment. Well, personally, I think it looks most like 6-2. I think it's 6-2. You see, look up there, and you see you're going over and then under and then over and then under with a little loop and then under and back over, and then there are two kind of turnarounds at the top and one at the bottom and 2 on the sides, and there's the loop and there's the 2 loops on the top. And if you follow the weaving pattern, it's alternating: under, over, under, over, under, over, under, over. And now you've been indoctrinated into that picture, and you probably can't see it as being unambiguous anymore. But indeed, that appears to be 6-2, and so we found that DNA can be knotted in the form of 6-2, but of course it can be knotted, depending on the experiments, in the form of many, many, many small knots. And let's go on with this notion. There is a kind of experiment that people can do with DNA and then watch the results, which is called processive recombination. And you have a DNA molecule here, and now I've drawn, this has to do with idealizations of things. I have drawn a single line, and that single line, with its twistiness, is meant to represent double-stranded DNA, like those photomicrographs, okay? So I've ignored everything except the topological structure of it. And here's this little 3 twisted Mobius, excuse me, I want to say Mobius, but it's not. 3 twisted DNA, and let's suppose that it moves around a little bit and this part can interact with this part. And it has been, in fact, prepared so that this part can interact with this part to be cut by an enzyme and crossover connected like that. That kind of thing can happen. Oh, but then there's a question about it. The question is the crossover connect from left to right or from right to left? Is it twisting this way or is it twisting that way? And this is an actual question that could be asked about an experiment. It could be known in an experiment that it's one way or the other, but the only way you're going to be able to find out is to look at the products of the recombination. And one can set up the experiment so that a recombination happens here, and then farther along the DNA another recombination can happen, and I indicated it here, and then farther along from here to here another one happened, and then with much less probability another one. But you could get a series like this so that what comes out is twisted, then twisted again, then twisted again, then twisted again. And if it's reliably twisting from left to right like that, well then it would do it the same way each time, and you would get this extra twist going on. Of course, you can then, up at this level of drawing pictures, take a look at the products. At the beginning it's unknotted, then here it's really that link that I drew on the right. You see that? That little circuit is separate from the other circuit, and it can be pulled in, and it looks like that. a simple link, the simplest possible linking of two curves. The next one changes that into a figure-8 knot. You can have fun yourself tracing how that is equivalent to this by pushing it around a bit. And then you get a link again, this interesting little link here, and then you get a knot again. So you could imagine these products coming out, and then you could do that DNA experiment again with the electron microscope and see them, and people did that. And they would see in a particular experiment carefully designed that a certain series of knots would come out. And that series of knots was concordant with the twist having been this way and not the other way, and thereby determine that the twist was that way with good evidence. But the evidence is a magnification of what happened and is invisible to direct sight, a topological magnification of that. So this became a way of interrelating topology with the study of DNA, and I won't say more about formalization or models of this, but you get the idea here. And it really does correspond to various problems that are going to be hard to ask, like exactly what series of knots would you get out? What if you really didn't know what this was going to be? Maybe it isn't known that it's one twist over. Maybe it's known that it's some number of twists over, but which number? And you see, you can still do this kind of analysis. The crudest kind is to just write out all the possibilities and see what they look like. And you may be able to do something subtler than that if you're clever. Now, here's another topic. This is the topic of knotted vortices. And I'm going to be telling you about some work by William Irvine and his student Dustin Kleckner at the University of Chicago not so long ago. And what they did was they figured out how, in a scientific context, to blow a knotted smoke ring. Now, you know how to blow a smoke ring, and you even live in a society where people are allowed to smoke, so you could do it. In the United States, it's a little harder to manage to blow smoke rings these days. But you know how to blow a smoke ring. You have the smoke in your mouth and you go like there, and the air and the smoke go past your lips held round, and vortexing occurs at the edge of the lips. So you can do the same thing by putting smoke in a box with a hole in it and hitting the back of the box, and smoke ring will come out the front. So how would you blow a knotted smoke ring? Well, it was a puzzle, and it used to be the sort of puzzle that knot theorists would wonder about to each other over dinner or at the bar. But these guys figured out how to do it. And maybe you will find that their solution is a little strange, because what they decided to do was to use a knotted form of lips. So no animal is going to be able to do this. But if you had knotted lips and you could blow the smoke ring past the knotted lips, then forward, out beyond that, would come a knotted smoke ring, right? Well, they made a knotted form like this, you see? The idea is that the basic cross-section of the form looks like this, an airfoil, and so then as the air goes, water in this case, goes past it, it can vortex. And it goes around in a knotted form like this, and then you give it a push or pull it back through the water, which is in fact what they do, and on the other side of it will come a knotted ring like this. And if you used the same kind of form with unknotted, then you'll get a vortex in the water that is unknotted like that. And that's the idea, and it worked. And one of the key things in making it work for them was that, along with thinking about how to make such a thing and maybe doing some mathematics about the design of it, they could then make one out of plastic using 3D printing and tinker with it that way until they got it to really work. And that's what they did. So here is an unknotted one. High-speed photography, good technology, everything. And here is a knotted one. And the photography is kind of crucial because you see, by having that good photography, you can see that it really is forming a trefoil knot. What happens next? I didn't somehow get hold of a film of what happens next, but you can imagine that what happens next is that it starts to break up. But it breaks up in a particular way, and I think I have a film that illustrates this with a model that I have next. Let's take a look. Yeah, all right. This is using mathematical fields to model the vortexing. And you see what happens is that it will break up into unknotted loops. And let's look at that again. It has to dock next to itself in a certain specific way in order to reconnect the way it did. And I just realized that I should have drawn a nice slide showing the reconnection, but I will try to do it with my fingers, all right? So you have two parts of it coming together like this, and then they reconnect like that. So it's a little like the DNA reconnection, but there's no crossover exactly. This reconnects like that. But now remember, it's a vortex, and that means that there's vortexing going around the line of it. And you need to have the other vortex coming along with the vortexing going around the line in the opposite direction in order for these to add up correctly and manage to do this and reconnect. So the reconnection looks like this vortex direction, and it reconnects like that. And we just saw how a trefoil knot might reconnect in 3 places and end up being 2 unlinked circles. Let's take a look at this a little more closely. Well, here's another movie. These movies are due to Irvine, using this kind of field modeling. And here what happened was that we started with the knot 6-2. That projection is a little hard to look at. I'll draw you a picture of it. And then it undergoes a recombination and ends up a reconnection and becomes this link. And then this link undergoes a reconnection and becomes a trefoil knot. And the trefoil knot undergoes reconnection just as we are about to see in another slide and becomes 2. And those 2 become 1. So it took 4 reconnections to find itself at the unknot. And you see that there's a nice question here, which is how many reconnections do you need in order to land on an unlinked collection of circles? You could, as you are going along, end up on something that is linked, and then you have to continue to reconnect. Or you might end up on a knot, and you would have to reconnect, and then it might be a link again, and so on. So it might take you a while to reconnect. And what's the most efficient pathway? And will nature take the most efficient pathway, where nature in this case is this model, but nature in the other case is the vortex in the water. So here's some drawings. I started with a trefoil knot, and I want to do a reconnection. And this is the vortex direction, so you can think of the vortex as going around like that. And this is going in the opposite direction from this if you brought them up parallel to one another. So that one is going this way and this is going this way. So these can reconnect to, this can go like that, and this one can go like that. And that's what I've drawn here. So this is a reconnection from here to here. And we end up with a link. That's one reconnection. We end up with a link. We have to keep on going if we're going to get unlinked or unknotted. And so I do one more somewhere here. These 2 are going in the opposite direction. And I do one more, and I get a little curl there and a little curl there, and it's unknotted. And so it took me 2 reconnections to undo the trefoil. Now, in the picture, you saw 3 reconnections. That's interesting, and you ended up, let's go back to the picture. I'm finding it amusing to look at this. Here you went to 3 reconnections, seemingly simultaneous, and you ended up with 2 loops. But you didn't really need 3 reconnections to get down to unknottedness. It just happened that way in this modeling. You only needed 2, and you would end up with this unlinked circle, single circle. Now over on the right, I've presented a point of view that I'm using to think about this. I say, think about the world line of this object. This is happening in time. In time it was this, then a little later time it was this, a little later time it was this. And I've drawn a schema for you of what happened. You see, you started with 1, and then you went through the recombination, and you ended up with 2. And then you ended up by recombining them again, reconnecting them again, and these 2 became 1 again, and you ended up with 1. And in time, what was traced out in 4-dimensional space, space-time, was a surface. And at the top surface, there was, of course, I'm only drawing the schema. At the top surface, there was this, and then it went through the process of recombining and reconnecting into 2, which is like going through a little saddle point, starting here, and here's the saddle point, like that, and turning into 2. And then these 2 go through a saddle point and come back into 1. You trace out a surface in 4 dimensions. And I'm interested in the genus of the surface. How many holes does the surface have? So here you can count. There's 1 hole, and you see that 1 hole has a maximum and a minimum in it. Each one, the maximum and the minimum, correspond to reconnections. So in a minimal sense, every hole has to correspond to at least 2 reconnections. So if I know the genus of the surface, then I have an estimate about the number of reconnections. If I know the surface has 2 holes, I know that at least 2 reconnections happened. If I have a surface with 3 holes, then I know that at least 6 reconnections happened, and so on. So we can examine the genus of the surface if we knew about it, and then we would know something about the number of reconnections. So the abstract geometry of this business about the surfaces is this. Here's a saddle. That's what I mean, you see. And a reconnection from this to this can be filled in with a bit of saddle in between. And it might go one way or the other. Sometimes also you might have a circle die out in mathematics, but in these models I don't worry about the surface circles dying out. They can dissipate. And getting born is even harder. But in mathematics we think of all the things that can happen with the surfaces. And then you see in the mathematical picture you might have an evolution that looked like this. It went through a saddle, 2 circles were born, one of them died, and the other one continued on, and there are no holes in this surface. Or here, we had genus 1 because there's 1 hole. So that's the kind of picture that we think about when we think about it just purely mathematically. But for the purposes of thinking about reconnections, I ignore births and deaths and just think about how many saddles. And then saddles, as I say, are related to holes. So if I know the genus, then I know something about the number of reconnections. Now let's go back to 6.2. Remember 6.2? That was the longer demonstration, a longer movie demonstration. And if we do a reconnection right there, you see, it will turn into this. And that's what you saw in the movie. And then if you do another reconnection right there, you'll turn into this. And now it's a trefoil knot with some curliness on it. And that's the middle place in that movie. It got down to a trefoil. And then the trefoil went through an evolution just like the one we saw before, so I won't draw it again. But it took two reconnections in the modeling to get down to the trefoil knot, and then it takes 2 more reconnections to get from the trefoil knot down to nothing. And so it took 4 altogether, and that's what we saw. You see, it's just a small technical thing, but it's a big technical thing. We can draw these diagrams, and as a result, we can make descriptions that would be really impossible to do in words about various things that are going on. Now, here's a curious trick. something maybe only a mathematician would love. I can switch a crossing, all right? Now that's something that I'm interested in doing with knots anyway. How many crossings does it take to switch a knot and make it unknotted? Right? You have a complicated knot. By switching some of the crossings, you can actually unknot it. How many does it take? But here's the beautiful fact. A crossing switch can be accomplished with 2 reconnections. And I've drawn the picture. Here, I put a little curl here next to that crossing so I can use it. And here's a reconnection that's possible, so I do it. And now this is underneath both ways, and I pull it out a little bit, and then I push it back over onto the top. And then I go through another reconnection to take it back where it was, but now this is over. And the curl is switched. It started this way and it ended this way. So that's the method by which mathematically I can do a series of reconnection operations and switch a crossing. And in terms of the kind of surface that got created, if you think about it a little bit, you'll see that it was the same as putting one hole in. So we did a bit of genus in doing that. Well, why do I tell you about that? Because in the mathematical world, 6-2 can be undone by only 2 reconnections because of a curious fact that this crossing right here in the middle, if you were to switch it, gives you an unknot. You see that that's an unknot? Let me give you a moment. Some unknots are hard to see, but this one's easy to see. This guy here, he's unknotted. You can just pull this arc back a little bit, and it becomes 2 curly things, and you get rid of them, and it's unknotted. Right? So you see, I go through the procedure that was on the previous slide and get rid of it. And now I'm at an unknot, and I'm done. But from the point of view of the physical system that was doing this, that's too clever somehow. The physical system would have to, might find there isn't even the nice curl that would be needed to do the recombining. So who knows? Maybe there is a starting point for 6-2 in a physical model or physical system where it would go through exactly 2 switchings. But from the point of view of the cleverness of the method that I just used, it doesn't look like it's so likely. So what's the moral of that? The moral of that is that it's likely, and William and I would like to know more, that many of the physical sequences will be longer than the mathematical possible sequences. And so we'd like to know more about that. When is the physical system efficient, and how efficient is it? And for that matter, the physical systems look like they're always undoing these things and making them fall apart. But how do you know that? So these are some of the problems that are naturally related to thinking about vortices. I want to tell you one more small thing. I can get a lower bound, and I'm going to explain how. Let me define a couple of numbers. This is the most mathematical part of the talk, maybe. I'm going to let R of k be the least number of reconnections needed to transform a knot into a collection of unlinked circles. Okay, that's what we've been talking about. Like R of the trefoil knot is 2. You need 2. Then there is a certain classical number associated with knots and links called its signature. I won't define it. But the signature of the trefoil is -2, and the signature of good old 6-2 is also -2. And here's the result. That the absolute value of the signature is less than or equal to the reconnection number. That if you calculate the signature out to be absolute value 2, which is what happened in the trefoil and 6-2, well then you couldn't possibly reconnect with less than 2 reconnection moves. And the proof of it goes like this. The genus of the 4-dimensional surface that we've been talking about, twice that genus is less than or equal to the reconnection number. That's what I've been telling you, right? That every time you look at a hole, you need 2 reconnections. On the other hand, it's a fact in topology that the signature is less than or equal to twice the 4 genus. And that, of course, is something we can't go into. But then combine these 2 facts, and you see that the signature is less than or equal to the reconnection number. And that means that if you hand me a knot I will go off and calculate its signature, and I will tell you, well, you're not going to get it down with less than so many, right? And so that's the beginning of some possible further research in understanding this kind of question about how complicated is a knot from the point of view of reconnecting it. Now, knotted vortices themselves, and let's see, how are we doing in terms of time? Yeah. Knotted vortices themselves have a long history, and they go back to the 1800s, where Lord Kelvin had the theory that, that atoms, which were just beginning to be studied, were knotted vortices in the luminiferous ether. A nice theory at the time. And he began to study the properties of knotted vortices and all of that. And for a long time, that was a very popular theory. But then eventually people found they weren't able to prove the stability of these things. And anyway, the luminiferous ether started to disappear. And by the turn of the 20th century, the luminiferous ether under Einstein's hands had gone away. And these theories were no longer available as theories of atoms. But the idea is still around. The idea that maybe fundamentally at some level in microphysics there are knots and they're very important. But at what level would they be occurring? And how would they be occurring? So we want to talk about that a little. And then I had some pictures that I thought were interesting. Since that theory was popular for a long time, other people who were deeply interested in ideas and thoughts about how the universe comes to be had their own illustrations of the notion. For example, Ledbetter and Besant, who were meditation visionaries and founders of theosophy, had the notion of matter forming from spirit. And somewhere in that transition, the matter in their vision was forming in the form of knots and vortices, and they had this particular image. I don't know how they got this image. I wondered on drawing some knots whether any of the knots I knew looked like their image, and I found one at least that looks something like their image. Here is a knot and its equation. Meaning that the x-coordinate is this cosine with that frequency and so on. And it looks a bit like they're not, but who's to say that it's the fundamental knot of the universe or anything of the sort? But when you see a knotted form, it is interesting to wonder what kind of dynamics might have produced it or what kind of equations might have produced it. Then there are other if you start looking around and asking where do you see knotting, you might go all the way up to this, which you would find easily on the internet. People call this the DNA nebula. It's 80 light-year long formation, and it looks like a braid. And there's braiding in plasmas and many other situations. So knotting occurs in many different places. Here's an old paper, which in a way brings back the Kelvin idea, but in 1972, Herbert Jela wrote this paper called Flux Quantization in Particle Physics, and he had the idea that elementary particles, so now we're down at elementary particles instead of atoms, and he had the idea that elementary particles were quantized, knotted electromagnetic flux. And then with that idea, he wrote a qualitative paper where he suggests that the neutrino, it would be a trefoil knot, and of course the antineutrino would be the mirror image of that knot, and so on. And he had quarks and everything else in his model. Not very quantitative, so it didn't catch on as a theory because not much could be computed from it, but it was, he wrote a series of papers on this, and I met him, which is one of the reasons why I'm telling you the story. I met him long, long ago, maybe in 1974, at a conference in Louisiana State University on topology, which he had decided to go to. I think he was at George Washington University then. He was probably about 74 and very intense. And he carried with him not ropes like these on his belt, but catheter tubes, which are quite good for tying knots in them. And if you started to talk to him for a few minutes, he would take those tubes out and start explaining to you the micro world with the help of his rubber tubing. And it was fascinating. I'd like to talk to him again, but it's not likely. So jumping forward from his time, we have the following situation. Protons are made of quarks. Quarks are bound by gluon field. If you have in the nucleus, if you never see an isolated quark. If the physics makes quarks come apart, then a very strong field occurs between them, the gluon field, and they don't really separate, and the field has a kind of tube-like property. And if you make a proton-proton collision, then the quark-antiquark pair from the nucleus can be thrown far apart, and this long tube is there out in space, and it may, wind around and knot through itself. There's some probability of that, and the ends may come back together, and you would have a closed loop of gluon field, possibly knotted. So those are called glue balls, closed loops of gluon field, and the possibility that they're knotted has been considered by various people like Antoniemi and Buini and Kephart. And Buini and Kephart did a statistical analysis. They looked at the tables of energies of products in proton-proton collisions. And so there's a pattern of energies. And they thought, well, if some of these are knots, then maybe some complexity measure of the knot would correspond to the energy levels of these products in the proton-proton collisions. And so they chose one of the more interesting measures of complexity of a knot. And that measure of complexity, now we're coming right back to the most concrete thing, is how much rope do you need to make the knot? So I tie this knot in a bit of rope which has a diameter, so I can't, so if I use a very, very small amount of rope, because I have to turn it around on itself, I can't make a knot. If I use a little more, then there's just room to make the knot. So every knot has a length, a rope length, and the rope length, in order to define it correctly, has to be the length of the rope divided by the diameter, so you get a scale-free number, and that's called the rope length. So the rope length of a knot is a very beautiful, simple invariant of the knot, characteristic of the knot. And it's also incalculable at the present time. You can use a computer to approximate it, however, and so people like Jason Cantarella and others, Eric Gradin, and a number of people whom I should mention and didn't, and haven't, have calculated tables of rope numbers and have computer programs that will take a knot and pull it up tight. Well, so they used the rope lengths and compared them with the energy levels, and they found a good correlation, and they're still working on that. So this is very indirect. Nobody can see that knotting, but they get good correlations between the complexities of knots coming from the tables and the energy levels of the products of the proton-proton collisions that are deemed to be gluons, glue balls. So here's a picture of contracting a knot to get to its rope length from Jason Cantarella's work. So you can imagine how this is working. There's a computer program that is taking off length and also expanding the radius without letting it cross through itself until you get into a nice tight form, just like you might by pulling on the rope and jiggering with it until you get a nice compact form. And by the time you get into this very nice compact form, you have arrived at certain fundamental geometric characteristics of the knot that are really characteristic of the knot and tell you something about it independent of how you had started. And that may be related to its possible energy level if it were a glue ball. I'm just showing you the citation here. And since I like this, I have another one. This is the knot 942. 942 is a beautiful knot, as you see. If it weren't for the clasp in the middle, it would be a figure 8 knot here, and a trefoil knot there, separated, but you start doing that kind of thing and you get more and more complexity. And that's just the beginning of the complexity that's going to be happening as you make larger and larger knots. And here's the contraction of that. So you see, this could become a hobby or an obsession with you if you were interested in it. You don't have to do this with a computer. You could just take a nice piece of rope like this and tie a knot in it and then try to, jiggle it until you get it into its least form and estimate how much rope you needed in order to make it. Now another topic, going farther down in the hierarchy of size. Sundance Bilson Thompson wrote a paper in which he suggested that the fermions, like the electron and certain quarks and neutrinos and so on, were modeled by not knots but braids. These are braids. A braid is what you think it is. It's braided strands, only his braids are made out of little ribbons as well, so they can twist. So there's braiding inside the braiding. The little plus sign means it's twisted by 360 degrees, the flat braid itself. So let me see. I just want you to understand what I'm saying. I think it's obvious, but the braids are made out of things like this, but they may be twisted like this. So when it says plus, it means it's got a 360 degree plus twist in it. And when it says minus, there's a corresponding twist in that. And then braids are very nice objects in that you can multiply them to get other braids. You see, you take this guy and you stick him onto this guy and meld them together right there and remove the blocks. The blocks mean you're not allowed to move it at that point. You can move it in the middle, but you can't move it at the top and the bottom. But you put these two blocks together and then remove the blocks, then what would you see? You'd see plus going on down, that is connected, and over here to minus. Plus cancels minus, and this slips right over to the right. This one, plus connected to minus, slips over to the left, and this one goes right down into the middle. So you see, if you multiply an electron times an anti-electron in his model, you get just straight lines. Well, that's the annihilation of the particle and the antiparticle, okay? But what about other interactions? Well, he found that other interactions could be modeled by his frame braids. So, for example, here we have a muon in his model, and then we factor it into a muon neutrino and a W minus particle, and then we do a little topology on this one, pushing these across from one another and factor it further, and we get a muon neutrino, an electron neutrino, and an electron. And that happens to be one of the possible particle interactions that do happen. Now, I have not done my scholarly job on his model and tried out, but one should, and I should, and maybe you should, go to a book on particle physics and get a list of all the fermion interactions and see if they all happen in this model. If they did, then we would be more astounded than we are. But he didn't do that in his paper. He should have done that. He should have done the scholarly job of writing down every possible interaction and maybe shown that the model, as is likely, doesn't quite model everything. Maybe it doesn't. But you'd like to know the limitations. So this is a curious thing, is it not? That you may be able to model the elementary particles by some topology coupled with some algebra. And where in physical space is this happening? This is algebraic. Now, of course, everybody is used to physics being rather algebraic or abstract, so it doesn't bother a theoretical physicist to say, well, I'll model the particles by this kind of algebra, but then if the algebra really works, then you want to go deeper and understand what's the context that would inform that. So we tried a little in a topological way. Now this isn't us. Us was a couple of people, and Sundance himself, myself, and but the theory became popular for a while, and these are the very nice illustrations that were drawn for a magazine, New Scientist, showing, but there's an idea here. You see, this idea came from a paper that Lee Smolin and Fotini Markopoulou and Sundance wrote. They said, well, why should these things be just isolated like that? Couldn't they be part of a topological network? So if they were part of a topological network, it would be like a surface. You see, here's this surface which is going on and touching many other parts of surface in 3 space. But here, localized on the surface, is one of those braids, and it's been capped off like that. And there's a positron, and here's an electron. But this leads to a problem, because the surface is subject to topological deformation. It can move around. So this apparently localized a positron sitting in the surface, after a little topological deformation, would start dissipating all over the place. So we don't know. But the question is, how much of this, how much of the properties of this would be retained if you started allowing this to move topologically? Well, this leads to some things that have to do with very concrete braiding. I think I have, so let's just go to the next slide. Here is a well-known method for making a braided belt. Have you ever done this? Have you ever owned a braided belt? A braided belt, if you bought one, consists of a strip of leather with 2 slits so that it has 3 bits of belt in the middle. And it hasn't been cut in any other way, but it's braided. How did the braiding happen? Well, the answer is that you start braiding it. If you're making one, you braid it for a while, and you get an anti-braid down below. So after a while, you get enough braiding, and then you take the bottom part and you twist it up through and get rid of the anti-braid at the bottom, and you end up with just the braiding. So topologically, this guy here is topologically equivalent to this guy over here. And every 6 half twists, you don't get any extra twist on the pieces of belt. You don't want the little pieces of belt to have twists on them. So there's a bit of craft here that produces a braided belt. So that means that these particles here, back up here, can undergo those kind of transformations, just as in the braided belt. You can start taking the top of this and pushing it through and changing the braiding. And we investigated for a while what would be left over after you did a lot of topological transformations like that on these, formalizing the kind of twisting that makes the braided belt like this. And we found that some things are left over, but it ended up in a big question mark. Perhaps all of this ends up in a big question mark. Now, I have one more comment to make. I think we should stop. But we could have stopped here with this question. But I want to show you one more thing. Let's skip this one, though, and go to this one. I like this one for its universality. It's been suggested that the 3-dimensional geometric universe is a 3-dimensional space of some sort. And that might be like this. Imagine that the walls of this room were in communication with one another, so that if you went through this wall, you would end up coming back through this wall. And if you went through the ceiling, you would come back through the floor, like in a 3D video game. Well, three-dimensional space might be like that. In that case, the three-dimensional space would be what topologists call the product of three circles. Or it might be a more complex and rather beautiful one where you take a dodecahedron like this and you have it so that when you go through this part, you end up back through here. So once identified, the walls are gone, and the universe has circular connectivities that go like that. And it's been theorized that the universe might be a dodecahedral space, or it might be some other three-manifold, with some people for a while plunking for the dodecahedral space and looking at the cosmic microwave background information and other information about sky to find out whether the statistics of that would coincide with it being that three-manifold. Now, what does this have to do with knots? Well, it does have something to do with knots. If you take a dodecahedral space made in that way, then it has some interesting symmetries. For example, you could rotate it by a five-fold symmetry around this axis, right? And so the universe would have a five-fold symmetry around that axis. Axis, well, if going from here to here and then you're right back here, that's a circle. So there would be a great big circle going through the whole universe, and the universe could turn around that circle with a five-fold symmetry. And what would happen if you identified a point that was 1/5 of the way in the rotation with its mate? So then the universe would be divided into 5 sectors, and you would only take one of them and you would make a further identification and collapse the universe. Well, the answer to the question of what would happen if you did that, if you used that, is that the big circle that goes all the way through the universe would become a trefoil knot sitting inside the three-sphere. The collapsed universe would be a three-sphere, and there would be a trefoil knot going all over the whole universe, which was the image of that axis. I know that's hard to visualize. I don't know how to visualize it well myself, but I'm saying that if you made this space by identifying the QPTSR, the upper plate with the lower plate and all the plates together, and you take the axis which goes straight down here, and you then collapsed it a little further by the five-fold symmetry, then you would end up with a trefoil knot inside that was the basis of this construction of the universe. So speaking in the opposite direction, which is the way we sometimes do in knot theory, we would say you start, to get the dodecahedral space, you start with the trefoil knot in the ordinary three space, and you form 5 special copies of that, and paste them together in a certain way, and you get the dodecahedral space, so that the trefoil knot is the creator of the dodecahedral space, which is the whole universe. And so from this point of view, it's the trefoil knot that might be the key to the universe. And that's a good place to stop, I think.